What if everything we've been taught about ancient civilizations is missing a crucial chapter? Picture this: artifacts buried for centuries, tools so advanced they defy logic, and inventions that shouldn't exist for thousands of years. Yet here they are, staring back at us like fragments of a lost world. These aren't myths or legends. They're real, tangible objects that challenge the very timeline of human progress. Today, we're pulling back the curtain on 24 astonishing tools, each one a testament to the ingenuity of our ancestors, each one rewriting history as we know it. Think about the last time you held a smartphone or marveled at modern engineering. Now imagine a device like the Antikythera Mechanism, a complex, gear-driven computer from ancient Greece that tracked celestial movements with pinpoint accuracy, or the Baghdad Battery, a clay jar capable of generating electricity 2,000 years before the light bulb. These weren't lucky accidents. They were the products of knowledge, skill, and innovation that somehow slipped through the cracks of time. How did they achieve such feats without the technology we take for granted today? What secrets did they know that we've only just begun to rediscover? This journey isn't just about uncovering old objects, it's about redefining what's possible. From self-healing Roman concrete that still stands strong after millennia, to Damascus steel swords with molecular structures we can't fully replicate, these tools aren't relics of a primitive past. They're evidence of a sophistication we're only now beginning to understand. And here's the most thrilling part: every discovery raises new questions. Who were the masterminds behind these inventions? How much of their wisdom has been lost to time? And what could their forgotten technologies teach us about solving today's challenges? Strap in, because by the end of this exploration, you'll never look at history the same way again. The past is far more mysterious and far more advanced than we ever imagined. Buried beneath the waves for over 2,000 years, the Antikythera Mechanism was discovered by sponge divers in 1900 and one near a Greek island. At first glance, it looked like a lump of corroded bronze, but when researchers carefully examined it, they uncovered something extraordinary: a complex system of interlocking gears, precisely calibrated dials, and inscriptions detailing celestial movements. This wasn't just an ancient artifact. It was a meticulously engineered machine, one that could predict solar eclipses, track the cycles of the Olympic Games, and even chart the positions of planets with stunning precision. What makes this device so remarkable isn't just its complexity. It's the fact that nothing even remotely similar appears in the historical record for another 1,000 years. The craftsmanship rivals Renaissance clockwork, yet it was built around 82 BCE, long before the concept of mechanical computers was thought to exist. The mechanism's gears functioned like an intricate cosmic calculator, using mathematical ratios to model the irregular motions of the Moon and the 5 known planets at the time. One of the most baffling aspects is how the ancient Greeks achieved such precision without modern tools. The teeth of the gears were cut by hand, yet they fit together with near-perfect accuracy. Some researchers believe the mechanism was just one of many, part of a broader tradition of advanced engineering that was later lost to time. It's possible that similar devices existed in libraries like Alexandria, only to vanish in fires or wars, leaving this single surviving example as a cryptic clue to what once was. The implications are staggering. If this technology was widespread, how did it disappear for centuries? Did later civilizations simply forget, or was the knowledge deliberately suppressed? The Antikythera Mechanism forces us to reconsider not just the timeline of human innovation, but the very nature of progress itself. Perhaps the ancients weren't just stumbling toward discovery, they were mastering concepts we still struggle to fully understand today. Buried in the sands of ancient Mesopotamia lies a puzzle that could rewrite the history of electricity: the Baghdad Battery. Discovered in the 1930s near what was once the thriving city of Ctesiphon, this unassuming artifact consists of three simple components: a clay jar, a copper cylinder, and an iron rod. At first glance, it looks like nothing more than a storage vessel, but when scientists reconstructed it, they made a startling discovery. Filled with an acidic liquid like vinegar or grape juice, the setup generated a small but measurable electric charge, somewhere between 1 and 2 volts. That's enough to power a tiny light bulb or, as some researchers speculate, to electroplate gold onto silver objects, a technique known to exist in the region at the time. The implications are mind-bending. If this was indeed an early battery, it predates Alessandro Volta's celebrated invention by nearly 2,000 years. But here's where the mystery deepens. No written records from the Parthian or Sasanian eras mention such a device, leaving us to wonder, was this a one-off experiment or part of a broader, undocumented tradition of electrical knowledge? Some historians argue it might have been used for medicinal purposes, akin to the way ancient Greeks applied electric fish to numb pain. Others suggest it could have played a role in religious rituals, perhaps creating a tingling sensation to simulate divine contact. What's most fascinating is the craftsmanship. The copper cylinder was perfectly soldered with a lead-tin alloy, a technique that wouldn't become common until centuries later. The iron rod, carefully insulated with asphalt, shows an understanding of conductivity that seems impossibly advanced for its time. Yet without clearer evidence of its use, the Baghdad Battery remains an enigma, a tantalizing glimpse into a technology that either faded into obscurity or was so ahead of its time that we're only now beginning to grasp its significance. Could there have been an entire branch of ancient science dedicated to electricity, lost to wars or the passage of time? The absence of similar finds makes it hard to say, but one thing is certain. This humble clay jar challenges our assumptions about the timeline of human innovation. It forces us to ask what other secrets might still be buried, waiting to reveal just how much our ancestors truly knew. The Pantheon's dome has stood unbroken for nearly 2,000 years, a silent witness to the unmatched durability of Roman concrete. While modern bridges and buildings crumble after decades, ancient Roman harbors still resist the pounding waves, their submerged structures growing stronger with time. The secret lies in a recipe so advanced that scientists are only now beginning to crack its code. Unlike today's concrete, which relies on Portland cement and cracks under stress, Roman builders mixed volcanic ash from the Pozzuoli region with lime and seawater, creating a chemical reaction that defies the ages. What makes this material extraordinary isn't just its longevity, it's its ability to self-repair. When microscopic cracks form, rainwater seeping in reacts with the volcanic ash to form new mineral growths, effectively filling the gaps. Modern experiments have replicated this process, confirming that seawater, far from corroding the concrete, actually activates its healing properties. Researchers call it the ultimate green building material, a sustainable alternative that could reduce the carbon footprint of today's construction industry by eliminating the need for constant repairs. The Romans didn't just stumble upon this formula by chance. Their engineers meticulously documented mixtures for different environments, harder aggregates for foundations, lighter pumice for domes, and even variations in ash composition depending on the region. The Pantheon ceiling, for instance, uses progressively lighter concrete as it ascends, distributing weight with precision that modern architects still admire. Yet after the fall of Rome, the recipe vanished for centuries, lost in the chaos of empire's collapse. Now, scientists are racing to reverse engineer this ancient technology. The challenge: modern builders lack access to the specific volcanic ash the Romans used, and reproducing its unique mineral structure remains elusive. Some teams are experimenting with fly ash from coal plants as a substitute, while others are tweaking seawater ratios to mimic the ancient chemical reactions. One thing's certain: unlocking this 2,000-year-old secret could mean skyscrapers that stand for millennia, sea walls that strengthen with storms, and a revolution in how we build our world. The irony is profound. The future of construction might depend on deciphering a wisdom we forgot long ago. The legendary blades of Damascus steel weren't just weapons, they were masterpieces of metallurgy, forged with techniques that modern science still can't fully replicate. Originating in the Middle East around 300 BC, these swords possessed an almost mythical quality, capable of cleaving through armor with ease and bending without breaking. What set them apart wasn't just their strength, but their mesmerizing surface, rippling with watery patterns that looked like frozen silk. These weren't mere decorations, they were the visual signature of a material engineered at the atomic level. The secret lay in the steel's unique composition. Ancient blacksmiths started with ingots of wood steel, a high-carbon alloy imported from India, and subjected them to a painstaking process of heating, folding, and hammering. But here's where things get fascinating. Recent electron microscope studies reveal that Damascus steel contains carbon nanotubes, tiny, ultra-strong structures that weren't officially discovered until the 1990s. These nanotubes, woven into the metal's matrix, gave the blades their legendary flexibility and razor-sharp edge. Even more baffling, the smiths achieved this without modern temperature controls or precision tools, relying instead on centuries of trial and error knowledge passed down through generations. Yet by the 18th century, the art of making true Damascus steel vanished. Historians debate why. Some blame the disruption of trade routes that supplied Wootz ingots, while others point to the rise of gunpowder, which made swords less relevant. Whatever the cause, the loss was profound. Today's metallurgists have spent decades trying to reverse engineer the process, experimenting with trace elements like vanadium and rare earth metals to recreate those telltale patterns. Some have come close, but none have matched the originals. What's most striking is how these ancient craftsmen manipulated materials on a scale we're only now beginning to understand. They didn't just make swords, they engineered a nanostructured supermaterial, centuries before the word nanotechnology existed. The irony is rich. In our quest to build the future, we're still chasing the secrets of a past that mastered mysteries we've only just begun to name. Greek fire was the ancient world's most feared weapon, a liquid nightmare that clung to ships and men alike, burning even as it floated on water. The Byzantine Empire guarded its secret so fiercely that the formula vanished with the fall of Constantinople, leaving historians and chemists scrambling to decode its ingredients for centuries. What made it so terrifying wasn't just its flammability, but its defiance of nature. While ordinary fires could be doused with water or sand, Greek fire seemed to feed on attempts to extinguish it, hissing and intensifying like a living thing. The weapon's most famous use came during sieges, where it was launched from pressurized tubes mounted on ships or walls, spewing streams of fire that could engulf entire fleets. Contemporary accounts describe its eerie glow, some claiming it roared like thunder, others noting a sulfurous stench that choked the air. The psychological impact was as devastating as the flames themselves. Enemy forces often fled at the mere sight of the Byzantines' fire-bearing ships, knowing there was no defense against this unstoppable force. But what was it made of? The leading theory points to a volatile mix of crude petroleum from surface seepages near the Black Sea, combined with quicklime, which reacts violently with water to generate heat. Some recipes may have included resin or saltpeter to stabilize the mixture, while others speculate about secret additives like pine tar or animal fats. The real genius, though, lay in its delivery system. Byzantine engineers designed bronze pumps and sealed cauldrons to prevent premature ignition, showcasing a level of chemical engineering that wouldn't be seen again until the modern era. The mystery endures because the Byzantines took extraordinary measures to protect their advantage. Only a handful of artisans and the imperial family knew the full recipe, with production spread across isolated workshops to prevent leaks. Manuscripts hint at rituals and oaths sworn under penalty of death, ensuring the knowledge died with its keepers. Today, even our best reconstructions fall short. Modern attempts either lack the adhesive quality or fail to replicate the water-resistant burn. Perhaps the most haunting question isn't how Greek fire worked, but how much other advanced technology vanished with it. If something this potent could disappear from history, what else might we have lost? The flames are gone, but the fascination burns brighter than ever. High in the Andes, the stone walls of Machu Picchu stand as a silent marble blocks weighing tons, fitted together so precisely that not even a razor blade can slide between them. What's truly baffling isn't just the absence of mortar, but the way these stones curve and interlock like puzzle pieces, some with 12 or more angles, each cut to micron-level precision. Modern engineers struggle to explain how the Inca achieved this without iron tools, wheels, or even a written language to blueprint their designs. The conventional explanation, patient hammering with stone tools, falls short when you consider the mathematical consistency of the joints. One theory suggests they used a technique called solar softening, where sunlight focused through polished concave mirrors heated the stone surfaces just enough to make them malleable, allowing artisans to shape them like clay. Others propose they harnessed sound frequencies, vibrating the stones at resonant pitches to liquefy them momentarily, a concept that echoes modern acoustic levitation experiments. The logistics deepen the mystery. At sites like Sacsayhuaman, massive limestone blocks were transported from quarries miles away, some weighing over 100 tons. Without beasts of burden or wheels, the Inca likely moved them using a combination of log rollers, ramps, and manpower. But how they lifted and positioned them with such accuracy remains unanswered. Even more intriguing are the knobs left protruding from certain stones, which some researchers believe served as handles for manipulation, possibly with ropes or levers in a system we've yet to decipher. What's often overlooked is the purpose behind this precision. The walls weren't just aesthetic, they were seismic genius. Peru's frequent earthquakes shake loose conventional masonry, but Inca structures dance with the tremors, their interlocking stones shifting and settling back into place like a self-healing mosaic. This wasn't just craftsmanship, it was engineering tailored to survive millennia. The tragedy, the Spanish conquest shattered the Incas' oral traditions, leaving us with fragments of knowledge. Today, archaeologists scour colonial texts for clues, while masons in Cusco still use ancient techniques to repair original walls, their hands guided by muscle memory passed through generations. The stones whisper secrets. We're only beginning to hear proof that brilliance needs no blueprint, only a legacy etched in rock. Norse sagas speak of a magical stone that guided Viking ships through fog and storms, revealing the sun's position even when the sky was obscured. For centuries, historians dismissed these accounts as mere legend, until researchers stumbled upon a clue hidden in an Icelandic mineral. The so-called sunstone wasn't mythical at all. It was a piece of calcite, a crystal with a remarkable property. When rotated against the sky, it could filter polarized sunlight, creating a telltale pattern that pinpointed the sun's location with uncanny accuracy. Imagine a Viking navigator holding the translucent crystal up to an overcast sky. By turning it slowly, they'd watch for a subtle shift in brightness, a hidden fingerprint of sunlight scattered by the atmosphere. Where the light through the crystal appeared most uniform, that direction revealed the sun's position even at twilight or behind thick clouds. Experiments with replicas have proven it works with precision, often within 5 degrees of the actual sun. This wasn't just intuition, it was applied physics centuries before the principles of polarization were formally understood. What makes this tool extraordinary isn't just its ingenuity, but the implications for Viking exploration. With no magnetic compasses, a technology that wouldn't reach Europe until the 13th century, the Norse crossed thousands of miles of open ocean, reaching Iceland, Greenland, and even North America. Calcite's effectiveness near the Arctic Circle, where summer sun barely sets, suggests it was especially vital during long voyages under perpetually gray skies. Archaeologists even found a calcite crystal aboard a 16th century shipwreck, hinting that the technique endured long after the Viking Age. Yet the sunstone's full story remains tantalizingly incomplete. No Viking-era sunstone has ever been found in a navigational context, leaving room for debate. Some scholars argue that driftwood patterns or bird behavior might have supplemented the crystal's readings, creating a layered navigation system. Others point to sagas describing dark rocks that could also locate the sun, suggesting multiple minerals were used. The real lesson here isn't just about a crystal, it's about rethinking how we view ancient seafarers. The Vikings didn't just brave the unknown, they mastered it with tools that blurred the line between science and myth. Their sunstone wasn't magic, it was something far more powerful. Proof that observation and innovation could unlock nature's hidden compass, turning the sky itself into a guide. In the year 132 AD, a brilliant Chinese inventor named Zhang Heng unveiled a device that would change how the ancient world understood earthquakes, the world's first seismoscope. Crafted from bronze and standing nearly 6 feet tall, it resembled an ornate vase adorned with 8 dragons, each poised to release a bronze ball into the mouth of a waiting frog below. At first glance, it might have seemed like an elaborate art piece, but its true purpose was nothing short of revolutionary. When an earthquake struck, even hundreds of miles away, the device's hidden pendulum would sway, triggering one of the dragons to open its jaws and drop a ball with a resonant clang. The direction of the fallen ball pointed to the quake's epicenter, giving officials critical information about where disaster had struck. What makes this invention so astonishing isn't just its accuracy, it's the sophistication of its design. Modern engineers have recreated Zhang Heng's seismoscope using historical descriptions, and the results are staggering. Tests show it could detect quakes far beyond human perception, sometimes even before tremors were felt locally. The secret lay in its internal mechanism, a delicate inverted pendulum suspended in a column of liquid, designed to amplify even the faintest vibrations from distant tectonic shifts. Remarkably, this system anticipated principles still used in today's seismometers, yet it predated them by nearly 2 millennia. The real genius, though, was its practicality. In an empire as vast as Han Dynasty China, where timely disaster response could mean the difference between survival and catastrophe, the seismoscope acted as an early warning system. Historical records describe it detecting a quake in what's now Gansu province over 400 miles from the capital, allowing relief efforts to mobilize before messengers could arrive. Some scholars speculate the device might have also been used ceremonially. its dragons symbolizing imperial authority over nature's chaos. Yet the most haunting question isn't how it worked, but why such technology disappeared for centuries. After Zhang Heng's death, the knowledge to reproduce his seismoscope faded, leaving later dynasties to reinvent seismology from scratch. Only fragments of his original writings survived, and no intact device has ever been found. Was the mechanism too complex to pass down? Did wars or shifting priorities erase this branch of science? The answers may be lost to time, but the legacy remains a testament to human ingenuity's fleeting brilliance and a reminder that progress isn't always a straight line. One thing's certain, when modern seismologists trace their field's origins, they're standing on the shoulders of a visionary who heard the Earth's whispers long before the rest of the world learned to listen. The Great Pyramid's granite sarcophagus tells a silent but shocking story. Its interior walls bear drill marks so precise, so impossibly smooth, that modern engineers struggle to explain them without invoking advanced technology. These aren't rough gouges from primitive tools, but spiraling grooves with consistent depth and spacing, as if cut by a machine. Core samples extracted from similar Egyptian artifacts reveal something even more baffling. The drills that made them removed material at a rate that would require diamond-tipped bits, spinning at speeds rivaling modern power tools. How could a civilization without electricity or industrial machinery achieve such precision? One theory points to the Egyptians' use of tubular drills, copper tubes coated with abrasive sand or crushed quartz, rotated by hand or with bowstrings. But experiments with replica tools show this method leaves jagged, uneven marks, nothing like the glass-smooth surfaces found in ancient granite. The math doesn't add up either. To drill just 1 inch into granite using manual abrasives would take weeks of labor, yet Egypt's monuments show thousands of such holes, many in hard stones like diorite that rank 7 out of 10 on the Mohs hardness scale. Here's where the mystery deepens. Microscopic analysis of drill cores reveals striations that suggest the tools weren't just spinning. They were applying downward pressure equivalent to 2 tons of force while maintaining perfect alignment. Some researchers speculate the Egyptians might have harnessed a lost technique involving ultrasonic vibrations or chemical softening agents to weaken the stone before drilling. Others point to enigmatic artifacts like the schist disc, a thin, finely balanced stone object with spiral grooves that resembles a modern machined component. Could these be fragments of a forgotten high-precision workshop tradition? The most compelling clue lies in the debris. Drill cuttings from ancient Egyptian sites show particles so fine they resemble the slurry produced by diamond core drills today, hinting at abrasives far harder than quartz. Emerald or corundum dust might explain it, but no historical records mention such materials being mined or traded. This absence of documentation fuels theories that advanced machining knowledge existed in isolated priestly or artisan guilds, deliberately kept secret and lost when those lineages died out. What's undeniable is the Egyptians' obsession with perfection. From the laser-like straightness of pyramid corridors to the flawless polish on statues, their work displays a standard of accuracy that seems to defy their era's technological constraints. Perhaps the answer isn't lost super technology, but a mastery of simple tools pushed to unimaginable extremes, a testament to human ingenuity's power to bridge the gap between the possible and the miraculous. The stones remain, whispering of skills we're still struggling to decode. Deep in the rainforests of Mesoamerica, the Maya achieved something modern chemists wouldn't replicate until the 19th century, a stable, bouncy rubber that could withstand extreme use. While Charles Goodyear is often credited with vulcanizing rubber in 1839, ancient Mayan artisans had perfected their own version as early as 1600 BC. Their secret, a clever blend of natural latex from rubber trees and the sap of morning glory vines, a mixture that transformed sticky liquid into durable, elastic material through a process we're only now fully understanding. The Maya didn't just stumble upon this formula, they engineered it. By boiling latex with morning glory juice, rich in sulfur-like compounds, they triggered a chemical reaction that cross-linked the rubber molecules, making them stronger and more resilient. This wasn't a trivial discovery. Modern experiments show that the exact ratio of these ingredients mattered. Too little morning glory sap and the rubber stayed brittle, too much and it became overly soft. The Maya hit the perfect balance, creating materials tailored for specific uses. Their rubber balls, used in ceremonial games, could rebound with remarkable energy, while waterproof coatings for textiles and footwear remained flexible even in tropical downpours. Perhaps most impressive was their use of rubber as an industrial adhesive. At the ancient city of Tikal, researchers found pottery shards glued together with a rubber-based compound that still held strong after centuries. Even more astonishing, some Mayan rubber samples show evidence of being layered with fabric or fibers, creating early composite materials akin to modern plywood or reinforced plastics. These weren't just crafts, they were calculated applications of material science far ahead of their time. What's truly humbling is how this knowledge echoes in today's labs. Researchers studying sustainable materials now look to Mayan rubber as a blueprint for eco-friendly alternatives to synthetic polymers. Unlike petroleum-based rubbers, the Maya's recipe relied entirely on renewable resources, leaving no toxic byproducts. Yet for all its sophistication, this technology nearly vanished with the collapse of Mayan civilization. Spanish conquistadors, more interested in gold than chemistry, dismissed rubber as a curiosity, never realizing they were witnessing a polymer revolution centuries ahead of Europe's industrial age. The legacy of Mayan rubber isn't just about bouncing balls or waterproof cloaks. It's a testament to human ingenuity thriving in unexpected places. In the dense jungles of Central America, without formal laboratories or written formulas, artisans decoded nature's chemistry, turning sap into a substance that still fascinates scientists today. Their forgotten mastery challenges a stubborn myth that innovation is the exclusive domain of so-called advanced civilizations. Sometimes the most groundbreaking ideas emerge from the places we least expect, quietly waiting for the world to catch up. In the heart of Delhi, a 23-foot iron pillar stands as a silent rebuke to modern metallurgy, defying 16 centuries of monsoons, pollution, and oxidation without a single speck of rust. The Indian iron pillar isn't just an ancient artifact. It's a metallurgical masterpiece that left scientists scratching their heads until the late 20th century. While modern steel bridges and skyscrapers require constant maintenance to combat corrosion, this 4th century marvel has endured without protection, its surface still smooth and unblemished. The secret, a dazzling feat of chemistry hidden in its very composition. At first glance, the pillar's durability seems impossible. Iron, after all, is notorious for reacting with oxygen and moisture, forming the flaky red oxide we know as rust. But ancient Indian blacksmiths engineered a brilliant workaround by blending the iron with an unusually high concentration of phosphorus, nearly 1% of its total mass. This wasn't accidental. Recent studies reveal that the smiths deliberately used a unique forging process, hammering layers of high phosphorus iron together with charcoal in a series of controlled heats. The result, a self-protecting barrier of iron-hydrogen phosphate formed on the surface, just microns thick but impervious to corrosion. What's even more astonishing is how this technique aligns with modern discoveries. Only in the 1970s did scientists develop weathering steel. a material that forms a stable rust-like patina to shield itself, essentially mimicking the pillar's natural defense mechanism. Yet here's the twist. While contemporary metallurgists achieved this with precise industrial processes, the pillar's creators worked without laboratory equipment or chemical assays. They relied on empirical knowledge passed down through generations, refining their craft through observation and trial. The pillar's inscriptions hint at its origins. Etched in Sanskrit, they celebrate King Chandragupta II's military victories, suggesting it was originally erected as a victory monument, but the real victory lies in its construction. Unlike modern welded or cast iron, the pillar was forged from a series of meticulously hammered discs, each welded together so seamlessly that the joins are nearly invisible. This technique not only prevented weak points but also distributed stresses evenly, allowing it to withstand earthquakes and centuries of weathering. Debates still simmer among researchers. Some argue that Delhi's dry climate plays a role in the pillar's preservation, but identical iron artifacts from the same era elsewhere have crumbled to dust. Others speculate that ritual offerings of oil or ghee over centuries created a protective coating, though chemical analyses show no such residue, the most compelling theory. The Smiths understood something we've only recently rediscovered, that controlled impurities aren't flaws but tools. By embracing phosphorus, often considered a contaminant in modern steelmaking, they turned a weakness into a shield. Standing before the pillar today, it's hard not to feel a sense of awe, not just for its endurance but for the minds behind it. This isn't just a relic, it's a challenge to our assumptions about progress. While we've sent rockets to Mars and split the atom, we're still unraveling the wisdom embedded in this ancient iron sentinel. It whispers a humbling truth. Sometimes the past holds keys to the future we're only beginning to grasp. In the blistering heat of Iran's deserts, where summer temperatures routinely soar above 120 degrees Fahrenheit, ancient architects devised a cooling system so effective it rivals modern air conditioning without a single watt of electricity. The Persian windcatcher, or Baghdad, is more than just a tower rising from clay rooftops. It's a masterpiece of passive climate control, harnessing the laws of physics to turn scorching winds into refreshing breezes. These structures, some dating back over 2,000 years, work through a clever interplay of wind pressure and thermal dynamics. Tall, square towers capture even the faintest gusts, funneling them downward into buildings below. But here's the genius. As hot air descends, it passes over subterranean water channels called qanats, where evaporation cools it dramatically before it enters living spaces. Meanwhile, the tower's design creates a vacuum effect, sucking stale indoor air upward and out through vents, completing a self-sustaining cycle of ventilation. What makes windcatchers truly remarkable is their adaptability. In the coastal city of Yazd, where winds are strong, the towers are tall and open on multiple sides to catch breezes from any direction. In more sheltered areas like Kerman, they're shorter but wider, optimizing for slower air currents. Some even feature adjustable shutters, ancestors to modern dampers, that residents could tweak to control airflow intensity. The effect was astonishing. Interior temperatures could drop by 20 to 30 degrees compared to the outside, creating comfortable havens in otherwise uninhabitable conditions. The system was so effective that ice could be stored in underground chambers called yakchuls even during peak summer months, a feat that seems almost magical until you understand the science behind it. Modern architects are now rediscovering these ancient principles. In Dubai's sustainable city, windcatcher-inspired designs reduce energy consumption by 40%, while London's Pearl River Tower uses a similar concept for natural ventilation. Researchers at the University of Cambridge have even modeled how wind catchers could be adapted for high-rise buildings, using computational fluid dynamics to optimize angles for urban wind patterns. The irony is striking. As we grapple with climate change and energy crises, solutions are emerging not from futuristic tech, but from technologies perfected over 2 millennia ago. The true brilliance of wind catchers lies in their holistic design. They weren't standalone gadgets but part of an integrated ecosystem paired with thick mud brick walls for insulation, reflective surfaces to deflect sunlight, and courtyards designed to create cooling microclimates. This wasn't just architecture, it was applied environmental science, a testament to how deeply our ancestors understood their landscape. In an era obsessed with high-tech solutions, these silent towers whisper a different approach. Sometimes, the most advanced technology isn't about adding complexity, but mastering simplicity in perfect harmony with nature's forces. Buried beneath the ashes of Pompeii, archaeologists uncovered a trove of Roman surgical instruments, so advanced they could easily be mistaken for modern medical tools. The collection reads like a contemporary surgeon's inventory: scalpels with razor-sharp steel blades, finely toothed bone saws for amputations, and delicate forceps with scissor-like hinges for extracting arrowheads or stitching wounds. But what's truly staggering isn't just their sophistication. It's the evidence that Roman doctors practiced sterilization techniques over 1,500 years before germ theory became mainstream. Examinations of these instruments reveal telltale signs of heat treatment, suggesting they were routinely exposed to flame or boiling water between procedures. Some even bear traces of a vinegar-based solution, known for its antimicrobial properties, a crude but effective disinfectant. This wasn't guesswork. Roman medical texts like those of Galen describe meticulous wound cleaning protocols, emphasizing the importance of preventing corruption in injuries. They may not have known about bacteria, but their empirical observations led them to practices that aligned eerily with modern aseptic techniques. The precision of these tools speaks volumes about Roman medical expertise. A vaginal speculum found in the ruins of Herculaneum, for instance, features adjustable screws to dilate with controlled pressure, a design so functional it remained virtually unchanged until the 19th century. Similarly, their bone drills included protective guards to prevent overpenetration, showcasing an intimate understanding of anatomy and surgical safety. These weren't makeshift implements. They were the product of centuries of refined craftsmanship, with handles ergonomically shaped to reduce hand fatigue during lengthy operations. Perhaps most surprising is the breadth of procedures these tools facilitated. From cataract needles for eye surgery to urethral dilators for bladder conditions, Roman medicine tackled complexities we often assume were beyond ancient capabilities. Surviving frescoes even depict battlefield medics performing what appear to be cesarean sections, using hooked instruments remarkably similar to modern obstetrical tools. The line between myth and reality blurs when you consider that some gladiators survived wounds that would have been fatal without expert intervention, a testament to the skill of physicians wielding these instruments. Yet for all their advancements, Roman surgical knowledge faced the same fate as so many ancient technologies: fragmentation and loss. As the empire crumbled, much of their medical wisdom was preserved not in Europe but in the Islamic world, where texts like those of Galen were translated and expanded upon. It would take the Renaissance and centuries of rediscovery for Western medicine to regain this level of sophistication. Standing in a museum today, staring at these gleaming bronze tools, it's hard not to feel a sense of kinship with those ancient healers. Their scalpels crossed the same flesh, their forceps grasped the same shattered bones, their saws faced the same life or death urgency. The materials have evolved, but the human ingenuity behind them remains timeless. In these artifacts, we don't just see the roots of modern surgery. We see a mirror reflecting our own unending quest to mend, to understand, and to push the boundaries of what healing can achieve. Long before the roar of modern flamethrowers echoed across battlefields, Chinese warriors of the 10th century wielded a weapon so terrifying it reshaped the very nature of combat: the fire lance. More than just a precursor to contemporary flamethrowers, these bamboo or metal tubes packed with gunpowder unleashed a deadly combination of searing flames and shrapnel, turning individual soldiers into walking arsenals. Historical texts from the Song dynasty describe their devastating effect: jets of fire that could reach over 10 feet, paired with ceramic fragments or poisoned pellets that turned each blast into a lethal multisensory assault. What set these weapons apart wasn't just their firepower, it was their versatility. Early versions functioned like handheld explosives, but by the 12th century, artisans had refined them into reusable devices with sequential ignition systems. Some featured multiple barrels for rapid fire, while others were mounted on wheeled carts for siege warfare, creating what amounted to medieval heavy artillery. The psychological impact was as potent as the physical damage. Imagine facing a line of troops suddenly erupting in gouts of flame, their weapons screaming like dragons as they advanced. No wonder contemporaries called them fierce fire oil shields and evil fire arrows, names that hinted at the superstitious dread they inspired. The chemistry behind these devices reveals surprising sophistication. Recipes from the Wujing Zongyao, a military manual compiled in 1044 AD, detail gunpowder mixtures optimized for different purposes, some with extra saltpeter for longer burn times, others with added resins to make flames stick to targets. Researchers experimenting with these formulas found that the inclusion of iron filings created sparks that could ignite enemy gunpowder stores, while arsenic compounds produced toxic smoke clouds. This wasn't random tinkering. It was systematic weapons development. Centuries before the scientific method formalized such experimentation. Yet the fire lance's legacy extends beyond destruction. Its evolution directly led to the first true firearms, as engineers realized confined explosions could propel projectiles with unprecedented force. By the 13th century, some models had transitioned from spraying fire to firing solid bullets, a pivotal shift that would eventually give rise to cannons and rifles. Historians debate whether this transition was deliberate or accidental, but what's undeniable is how this tool of war became a catalyst for technological revolutions far beyond its original purpose. The most haunting question isn't how the Chinese developed such advanced weaponry, but why similar innovations didn't emerge elsewhere. While Europe still relied on swords and arrows, Song dynasty armies fielded weapons that foreshadowed modern combined arms tactics. The answer may lie in China's unique blend of centralized innovation and constant warfare, a crucible that transformed gunpowder from a curiosity into a game changer. Today, as we trace the lineage of modern firearms back through centuries of conflict, we're left staring at a simple truth. Sometimes the spark of progress comes from the very flames meant to destroy. In the bone-dried deserts of southern Peru, where rain might not fall for years, the Nasca people engineered a water network so resilient it still functions today, 2,000 years after its creation. These aren't simple ditches or surface canals, but a vast underground labyrinth of spiraling stone tunnels known as puquios, designed to tap into subterranean aquifers with almost magical precision. Unlike modern irrigation that relies on pumps and pipes, the Nasca aqueducts work entirely by gravity, guiding water through winding subterranean channels that prevent evaporation in the scorching heat. What's astonishing isn't just their longevity, but the sheer ingenuity behind their construction, a blend of geology, astronomy, and civil engineering that modern hydrologists are only beginning to fully appreciate. The aqueducts reveal their brilliance in the details. Vertical shafts, some plunging 50 feet deep, were dug at regular intervals not just for maintenance, but to harness the venturi effect, an aerodynamic principle where wind rushing over the openings creates suction, actively pulling water through the system. The tunnels themselves were lined with porous river rocks, allowing groundwater to seep in while filtering out sediment, but the real masterstroke was their placement. By studying star alignments and geological faults, the Nasca positioned these channels to intersect with underground veins of water, creating a self-replenishing supply that even droughts couldn't exhaust. Today, farmers in the Nasca Valley still rely on these ancient channels, their stone mouths gushing cold, clear water as reliably as they did when Rome ruled Europe. Modern attempts to replicate the system have failed miserably. Without the Nasca's intimate knowledge of underground hydrology, engineers either hit dry rock or flood their tunnels. Recent satellite imaging has uncovered even more complexity. The entire network forms a fractal-like pattern, with smaller channels branching off like capillaries to distribute water evenly across the desert. Perhaps most humbling is how these aqueducts redefine what we consider primitive. While Europeans of the same era were diverting rivers with crude dams, the Nasca were manipulating groundwater pressure and wind dynamics with the finesse of modern environmental engineers. Their legacy whispers a provocative idea. Perhaps survival in harsh climates doesn't require conquering nature, but collaborating with it. A lesson we're relearning today as climate change forces us to rethink water management. The Puquios aren't relics. They're a living testament to the power of observation, patience, and the quiet genius of civilizations who listened to the earth long before we thought to shout over it. Long before James Watt's steam engine powered the Industrial Revolution, a brilliant inventor in 1st century Alexandria was already harnessing the power of pressurized vapor. Heron, sometimes called Hero, crafted a deceptively simple device called the Eelipile, a hollow metal sphere mounted on a boiler with two bent nozzles protruding from opposite sides. When heated, the escaping steam caused the sphere to rotate at dizzying speeds, becoming what many consider history's first steam turbine. This wasn't just a curiosity. It was a working demonstration of thermodynamics principles that wouldn't be formally described for another 1700 years. The mechanics reveal startling sophistication. Water inside the sealed boiler turned to steam, traveling through tubes into the sphere before jetting out through the angled nozzles. According to Newton's third law, every action having an equal and opposite reaction. The force of the escaping steam created torque that spun the sphere. Heron's writings describe speeds sufficient to perform work, suggesting he recognized its potential beyond mere spectacle. Some historians argue he may have used similar principles to power automated temple doors, creating miraculous effects to awe worshippers. What makes the Eelipile truly revolutionary is how it represents a road not taken. Unlike Watt's later piston-driven engine designed for factories and locomotives, Heron's invention remained confined to philosophical circles and royal courts. The reasons are as complex as the device itself. Ancient Mediterranean societies lacked the metallurgical precision for high-pressure boilers, and with abundant slave labor, there was little economic incentive to develop mechanical alternatives. Some scholars speculate that without these constraints, Heron's followers might have adapted the technology for mills or ships, potentially triggering an industrial revolution during the Roman Empire. Modern engineers have recreated the Eelipile with fascinating results. Using materials available in Heron's time, replicas achieve rotations exceeding 1,000 revolutions per minute, enough to power small generators. This raises tantalizing questions. Could arrays of Eelipiles have been linked to drive machinery? Might incremental improvements have led to more efficient designs? The answers remain speculative, but the exercise highlights how cultural and economic factors often determine which technologies flourish or fade. Perhaps the most poignant lesson lies in Heron's own writings. Among his surviving works is a detailed guide to building automata, mechanical birds that sang and statues that poured wine, proving he saw steam's potential beyond raw power. In another timeline, his playful curiosity might have birthed an age of ancient robotics. Instead, the Eelipile became a footnote, its principles dormant until the modern era. The device stands as both an achievement and a reminder. Innovation requires not just brilliant minds, but societies ready to embrace their visions. As we marvel at this 2,000-year-old turbine, we're left wondering what dormant breakthroughs in our own time might future generations rediscover. 5,000 years ago, along the fertile banks of the Tigris and Euphrates, Mesopotamian artisans unlocked a secret that would forever change human creativity: the art of glassmaking. Far from the crude, cloudy beads one might expect, these early masterpieces shimmered with vivid blues, deep reds, and translucent whites, their surfaces etched with intricate patterns that still dazzle today. What's truly remarkable isn't just their beauty, but the sheer ingenuity behind their creation. Without furnaces capable of reaching modern melting temperatures or precision tools, these craftsmen developed techniques so refined that some of their methods remain mysteries even now. Take core forming, one of their signature innovations. Artisans would shape a clay core into the desired form, perhaps a perfume vial or an amulet, then dip it into molten glass like a candlemaker coating a treat. As the glass cooled, they'd painstakingly add colored threads or delicate dots, manipulating the semi-molten material with rods to create swirling patterns reminiscent of marble. The final touch, removing the clay core through a tiny opening, leaving behind a hollow vessel so thin and even it defies belief. Some surviving pieces show walls barely thicker than an eggshell, their symmetry perfect enough to rival machine-made glassware. But the Mesopotamians didn't stop there. Mold casting allowed them to mass-produce intricate designs, pressing softened glass into carved stone molds to create everything from jewelry to ceremonial bowls. What's astonishing is their understanding of chemistry. By adding cobalt for blue, copper for red, or manganese for purple, they achieved a palette as rich as any modern stained glass window. Recent analyses reveal some blue glasses contain traces of antimony, a metalloid that boosted brilliance, an additive modern glassmakers wouldn't rediscover until the Renaissance. Perhaps most intriguing are the ribbed vessels from their surfaces textured with precise ridges that catch light like prisms. Scholars still debate how these were made. Some suggest they used a lost wax technique similar to metalworking, while others propose they rolled hot glass over textured molds. What's undeniable is the skill involved. These weren't utilitarian objects, they were status symbols traded across empires from Egypt to the Indus Valley. A single necklace might contain hundreds of microbeads, each drilled with holes finer than a needle, a feat that would challenge today's jewelers. The legacy of Mesopotamian glass whispers a profound truth about ancient innovation. This wasn't just craft, it was science disguised as art. By trial and error, these early chemists decoded how silica, soda, and lime could transform into something both fragile and eternal. Their creations outlasted kingdoms, surviving wars and weather to remind us that brilliance isn't measured by the tools at hand, but by the vision behind them. In their shimmering depths, we see not just reflections of the past, but the glowing embers of a revolution that still illuminates our world today. Picture setting sail across thousands of miles of open ocean with no compass, no maps, and no GPS, just the stars above and the subtle language of the sea below. This was the daily reality of Polynesian navigators, who mastered the Pacific centuries before European explorers dared venture beyond sight of land. Their secret, an invisible tool more precise than any instrument, the star compass, a mental construct that transformed the night sky into a celestial roadmap. Unlike physical compasses that point north, this was a living system woven from astronomy, oceanography, and biology, allowing navigators to pinpoint islands smaller than a pixel on modern charts. At the heart of this system lay an encyclopedic knowledge of star paths. Polynesians memorized the rising and setting positions of over 200 stars, using them as fixed reference points. When the constellation Scorpius arched overhead in a certain way, it signaled the direction to Tahiti. Orion's belt might guide them toward Hawaii, but stars alone weren't enough. Navigators also read the ocean's subtle cues, the way swells refracted around distant landmasses, creating interference patterns detectable miles offshore. They observed how flocks of birds changed flight patterns at dusk, revealing unseen islands beyond the horizon. Even the color and temperature of seawater held clues, with certain shades indicating proximity to coral atolls. The true genius of this method was its adaptability. Unlike Western navigation, which relied on rigid coordinates, the star compass was fluid. If clouds obscured the stars, navigators switched to reading wave dynamics. If currents shifted unexpectedly, they interpreted the behavior of marine life, dolphins congregating in specific areas, or the sudden appearance of land-nesting seabirds at dusk. This wasn't just wayfinding, it was an ongoing dialogue with nature where every element became a signpost. Modern scientists have tested these techniques with astonishing results. In 1976, the voyaging canoe Hokulea sailed from Hawaii to Tahiti using only traditional navigation, a 2,500-mile journey completed without instruments. The navigator Maupiilug corrected course by feeling swells beneath the hull and tracking star bearings with his hand. When GPS logs were later compared to his estimated positions, the discrepancies were negligible. Similar voyages have since replicated these feats, proving this wasn't luck but a reproducible science. What's often overlooked is how this knowledge was preserved, not in written manuals, but through chants and stories passed down generations. Navigational lineages were sacred, with apprentices spending decades memorizing star sequences and wave patterns. The loss of this tradition during colonial periods nearly erased it entirely, until a handful of elders like Piilug revived it in the late 20th century. Today, their legacy challenges our assumptions about exploration. While Europeans were still fearing the edge of the world, Polynesians were crisscrossing an ocean twice the size of Russia, turning the Pacific into a highway rather than a barrier. The star compass wasn't just a tool, it was a philosophy. It required seeing the world as interconnected, where sky, sea, and wildlife formed a coherent whole. In an age obsessed with technology, this ancient wisdom whispers a radical idea. Sometimes the most advanced navigation system isn't built from silicon and satellites, but from generations of patient observation etched into human memory. The Polynesians didn't conquer the Pacific, they learned to listen to it, and in doing so, achieved what our instruments still struggle to match. In the ancient Mediterranean world, no color commanded power like Tyrian purple, a hue so rich it seemed to pulse with life, shifting from deep crimson to violet depending on the light. This wasn't just dye, It was liquid royalty, painstakingly extracted from the glands of tiny sea snails by Phoenician artisans along the coast of modern-day Lebanon. The process bordered on alchemy. Workers would crack open thousands of spiny murex snails, harvesting a mere drop of mucus from each creature. Left to ferment in saltwater and exposed to sunlight, this murky liquid underwent a miraculous transformation, gradually deepening into a shade that would come to symbolize divine authority across empires. The scale of production was staggering. Historical accounts suggest it took 12,000 snails to yield just 1 gram of pure dye, enough to color the hem of a single garment. Vats of rotting shellfish filled entire neighborhoods with a stench so potent that ancient writers described it as both nauseating and intoxicating, like the smell of power itself. Yet the result justified the effort. Unlike vegetable dyes that faded to dull browns, Tyrian purple grew more vibrant with age, its chemical structure bonding permanently to fabric fibers. A single purple cloak could cost the equivalent of a laborer's lifetime wages, ensuring only emperors and high priests could afford it. Roman senators weren't allowed full purple robes, only thin stripes as a nod to their status, while Byzantine emperors signed documents with purple ink, declaring their decrees literally written in royal blood. Modern chemists have unraveled some of its secrets. The dye's key compound, dibromoindigo, forms through a complex reaction between the snail's enzymes and sunlight, a photochemical process that wouldn't be replicated in labs until the 20th century. Even more fascinating, the exact shade varied by species and location. Murex brandaris produced reddish purples, while Bolinus truncatus yielded cooler violet tones, allowing master dyers to mix custom hues like ancient Pantone swatches. Carthaginian merchants guarded these variations fiercely, establishing trade networks that stretched from Britain to the Silk Road. But Tyrian purple's true legacy lies beyond chemistry or commerce. It became a political weapon. When Rome defeated Carthage, they didn't just burn the city, they confiscated its dye workshops, turning purple production into a state monopoly. Later, Byzantine emperors executed rivals caught wearing the color without permission. The dye's scarcity was deliberate. By controlling access to the hue of gods and kings, rulers turned a pigment into propaganda. Today, the beaches near Tyre still bear witness to this obsession. Layers of crushed murex shells stretch for acres, forming man-made hills that glow faintly purple in certain lights. These eerie mounds are the ghosts of an industry that shaped history, proving that sometimes the most powerful technologies aren't machines or weapons, but the mastery of turning the humblest creatures into symbols of immortality. The snails are gone, but their color endures a whisper from the past in every royal tapestry, every cardinal's robe, reminding us that human ambition can extract majesty from even the unlikeliest of places. For thousands of years before European settlers arrived, indigenous Australians shaped their environment with fire, not as destructive force, but as a precision tool for regeneration. Known as firestick farming, this ancient practice involved carefully timed, low-intensity burns that cleared underbrush while sparing mature trees, creating a mosaic of differently aged vegetation across the landscape. Unlike modern wildfires that rage uncontrollably, these cultural burns moved slowly and deliberately, guided by generations of accumulated knowledge about seasonal patterns, plant life cycles, and animal behavior. The results were landscapes that functioned like natural firebreaks, where biodiversity thrived in carefully maintained balance. The sophistication of this approach reveals itself in the details. Aboriginal elders timed burns to coincide with specific weather conditions, cooler months when humidity helped regulate flame intensity, or after rains when certain plants were most resilient. They read the land like a living calendar, igniting fires when bush tomatoes flowered or when particular bird species nested, ensuring flames would stimulate new growth just as ecosystems were ready to rebound. These weren't random acts of burning, they were ecological interventions as precise as modern permaculture, tailored to each unique terrain. In Arnhem Land, for example, clans created fire patterns resembling checkerboards, patches of recently burned land alternating with unburnt areas to provide diverse habitats. Kangaroos grazed on the fresh shoots in burned zones, while lizards and small mammals took refuge in the untouched sections, creating a self-sustaining cycle of abundance. Modern science is only now catching up to this wisdom. Researchers studying firestick farming areas found they contain 30% more mammal species than national parks where burning was suppressed. The practice maintained open forests that allowed sunlight to reach edible tubers and encouraged the growth of fire-resistant food plants like bush onions. Even more remarkably, these controlled burns reduced the buildup of flammable debris that fuels catastrophic wildfires, a lesson painfully relearned during Australia's devastating 2019 and 2020 fire seasons, when areas where traditional burning had been discontinued suffered the worst damage. What sets Indigenous fire management apart isn't just technique, but philosophy. Where Western conservation often sees fire as an enemy to suppress, Aboriginal cultures view it as kin, a creative force that renews rather than destroys. This perspective is encoded in Dreamtime stories where ancestral beings used fire to sculpt the land, teaching that human and natural systems must work in partnership. Contemporary rangers merging traditional knowledge with satellite mapping have revived these practices in places like Kakadu National Park, where carefully planned burns now prevent 80% of destructive wildfires while doubling populations of endangered species. The legacy of firestick farming challenges our assumptions about wilderness and progress. The pristine landscapes early Europeans encountered weren't untouched. They were meticulously curated over millennia. In an era of climate crisis, this ancient practice offers more than historical insight. It provides a roadmap for living sustainably on a fire-prone continent. The flames may have faded, but the knowledge endures, a testament to cultures who understood long ago that true stewardship means working with nature's rhythms, not against them. High in the Andes, the Inca Empire managed one of history's most complex civilizations without what we'd recognize as a traditional writing system, or so we thought. Enter the Quipu, an intricate web of knotted cords that served as far more than simple accounting tools. These colorful strings, some stretching over 6 feet long, contained a sophisticated language of numbers, patterns, and spatial relationships that modern researchers are only beginning to decipher. What makes Quipus revolutionary isn't just their existence, but how they force us to redefine what writing really means. Each quipu consisted of a primary cord from which dozens of pendant strings hung like a fibrous waterfall. The knots weren't random. Their type, position, and sequence followed precise mathematical rules. Simple overhand knots represented the number 1, while figure 8 knots stood for 0, a concept the Inca grasped centuries before it appeared in other numbering systems. The placement of knots along each string corresponded to decimal places, allowing record keepers to document everything from grain stores to astronomical cycles with base 10 precision. But here's where it gets fascinating. Recent analyses suggest some Quipus encoded non-numerical information too. Variations in cord color, fiber type, llama wool versus cotton, and even the direction of knot twists may have conveyed narratives, genealogies, or laws, transforming these devices into a full-fledged 3-dimensional writing system. The scale of this system was staggering. Spanish chroniclers reported warehouses filled with quipus during the conquest, suggesting they formed an imperial archive as comprehensive as any library. Local administrators used smaller quipus to track tributes and labor obligations, while royal messengers carried them across the empire's vast road network like bureaucratic text messages. Some scholars argue the arrangement of cords mirrored Inca social structures, with central strings representing the Sapa Inca and subsidiary cords symbolizing provinces, a physical manifestation of their worldview. Breaking the code has proven maddeningly difficult. Of the roughly 1,000 surviving quipus, most were cut from their original context by colonial looters, leaving researchers without crucial reference points. But tantalizing clues emerge from villages like Tupacosha in Peru, where elders still create quipus for ceremonial purposes, preserving ancestral knot-tying techniques. Linguists studying these living traditions notice striking parallels between Quipu patterns and Quechua grammar, suggesting the knots might encode syllables or concepts rather than letters. The implications rewrite history. If quipus truly functioned as writing, the Inca join a select group of civilizations who independently developed full communication systems. More profoundly, it challenges Eurocentric assumptions that advanced cultures must use alphabets. Perhaps writing doesn't require ink and paper, just a shared symbolic language, whether etched in clay, painted on silk, or in this case, whispered through the silent eloquence of twisted fibers. The Quipu's enduring mystery reminds us that human ingenuity manifests in countless forms, and some of our most profound stories may still be tied in knots, waiting for the right hands to unravel them. Amid the clangor of medieval battlefields, one weapon struck fear into the hearts of warriors across Europe: the Viking Ulfberht sword. These weren't ordinary blades, they were forged from a metal so pure, so advanced, that historians once believed they couldn't have existed in the Viking Age. Modern analysis reveals their secret: crucible steel, a material with carbon content nearly as uniform as modern surgical instruments, free from the slag and impurities that plagued contemporary European swords. The mystery isn't just their quality, it's how Vikings, often stereotyped as crude raiders, accessed technology that wouldn't become commonplace for another 800 years. The swords bear their maker's mark proudly, the word Ulfberht inlaid in iron letters on the blade, a trademark that signaled elite craftsmanship. Of the roughly 170 surviving examples, the finest specimens contain steel with a carbon content of around 1.2%, rivaling the best Japanese katana steels. When tested against replica weapons from the same era, Ulfberht blades flex without breaking, hold sharper edges, and require less maintenance, qualities that would have given their wielders a terrifying advantage in combat. Contemporary accounts describe them cutting through mail armor like cloth, their resilience bordering on supernatural in the eyes of foes. But where did this steel come? The prevailing theory points east, along trade routes stretching to the Islamic world. Crucible steel production was flourishing in places like Persia and Central Asia, where artisans mastered the art of melting iron with precise amounts of carbon in sealed clay crucibles, creating homogeneous ingots of ultra-high-quality steel. Chemical fingerprints in some Ulfberht swords match ores from modern-day Afghanistan, suggesting a vast trade network bringing raw materials or finished billets thousands of miles north. Other researchers propose a more startling possibility: that Viking smiths themselves developed localized crucible techniques, perhaps inspired by interactions with the Islamic world during raids or diplomatic exchanges. The forging process only deepens the enigma. Unlike pattern-welded swords of the time, where rods of iron and steel were twisted and hammered together, Ulfberhts were made from a single piece of crucible steel, heated and shaped with extraordinary control. Metallurgists note the blades show evidence of precise temperature management, likely achieved by quenching in oil rather than water to prevent stress fractures. Some even feature what appears to be a form of differential hardening, where the edge was cooled faster than the spine to create a perfect balance of hardness and flexibility, a technique later perfected by Japanese swordsmiths. What's most haunting is how abruptly the tradition ends. By the 12th century, Ulfberht production ceased, and Europe regressed to inferior steel for centuries. Was the knowledge lost when trade routes collapsed? Did political shifts disrupt the supply of exotic materials? The swords themselves offer no answers, only silent testimony to a technological peak that flickered brightly before vanishing into the mists of history. Today, as blacksmiths and historians collaborate to recreate these legendary blades using period-accurate methods, each spark at the forge whispers the same question: how much more might the Vikings have achieved if their secrets hadn't been swallowed by time? Centuries before the Montgolfier brothers made history with their manned balloon flight in 1783, Chinese inventors were already harnessing the power of heated air to conquer the skies, not with elaborate aircraft, but with deceptively simple lanterns. Known as Kongming lanterns, these delicate paper balloons, fueled by small oil lamps or candles, floated upward on the same basic principle as modern hot air balloons. Warm air rises, creating lift. But what began as military signaling devices may have evolved into something far more ambitious. Tang Dynasty texts hint at larger versions capable of carrying humans, suggesting experiments with manned flight that predate European achievements by nearly 1,000 years. The genius of these early balloons lay in their elegant simplicity. A bamboo frame stretched thin rice paper into a lightweight envelope, while a wax-soaked cloth or dish of oil at the base provided just enough heat to fill the lantern with warm air. Soldiers used them to send coded messages across battlefields. A single glowing dot ascending into the night could relay troop movements or signal distress. Yet some historical accounts push the boundaries of this technology. A 9th century chronicle describes a daredevil named Yuan Huangtu, who allegedly floated over a besieged city wall using dozens of lanterns tethered to a wicker seat, though historians debate whether this was fact or folklore. What's undeniable is the scientific sophistication behind these devices. Unlike the Montgolfier's balloons, which relied on burning wool and straw to generate massive heat, Kongming lanterns demonstrated an intuitive grasp of thermodynamics using minimal fuel to achieve maximum lift. Modern recreations show they could reach altitudes exceeding 3,000 feet, with flight durations of over an hour under ideal conditions. Even more impressive. The lantern's design naturally stabilized them in flight. As heat escaped through the open base, cooler air was drawn in, creating a self-regulating cycle that prevented the paper from igniting. This wasn't just trial and error, it was applied physics disguised as folkcraft. The most tantalizing clues come from Ming Dynasty illustrations depicting elaborate aerial platforms suspended from clusters of lanterns floating observation decks that may have been used for reconnaissance or ceremonial purposes. While no physical evidence survives, these drawings align with contemporaneous reports of firebirds seen hovering over imperial palaces. Some scholars speculate these were test flights for human-carrying systems, perhaps abandoned due to the inherent risks. After all, without modern fireproof materials or precise altitude control, a single errant spark could turn a balloon into a death trap. The legacy of these early experiments lingers in unexpected places. During World War II, Japanese forces attempted to weaponize Kongming lantern principles, launching thousands of paper balloons carrying incendiary devices toward North America via jet streams. Centuries earlier, Chinese strategists had envisioned even grander applications. One military treatise proposed using lantern arrays to lift entire spy platforms behind enemy lines. Though these ambitions outstrip the technology of the time, they reveal a startling truth. The dream of human flight wasn't born in 18th century France, but in the workshops and battlefields of ancient China, where paper, fire, and ingenuity briefly opened a window to the skies. Today, as lantern festivals light up nights across Asia, each floating glow carries echoes of that forgotten ambition. They're more than decorations, they're the last whispers of an alternate aviation history, one where humanity's first steps toward flight weren't measured in horsepower or altitude, but in the quiet wonder of a paper lantern rising effortlessly into the dark, proof that sometimes the simplest tools hold the most revolutionary potential. The black-rimmed eyes we associate with ancient Egyptian royalty weren't just about looking striking, they were a brilliant fusion of medicine, spirituality, and cutting-edge chemistry. Kohl, the iconic eyeliner worn by pharaohs and commoners alike, contained a powerful blend of galena, lead sulfide, and crushed minerals that recent studies reveal functioned as a formidable antibacterial shield. Modern lab tests show these formulations actively protected against eye infections like conjunctivitis, which thrived in the Nile's flood-prone environment. But the real surprise, the lead compounds, long vilified for their toxicity, may have actually stimulated the immune system when applied topically at low doses. A paradoxical effect that's forcing scientists to reevaluate ancient medical wisdom. Egyptian cosmetic jars tell a deeper story. Excavated pallets from tombs contain residues of green malachite, another antimicrobial, while red ochre pigments mixed with animal fats created early sunblocks that shielded skin from the desert sun. The famous bust of Nefertiti showcases more than artistic mastery. Her layered makeup reflects precise recipes, with different mixtures for daytime wear, lighter, reflective minerals to deflect sunlight, and ceremonial use, darker, shimmering blends infused with sacred resins. These weren't vanity products, they were pharmaceutical toolkits disguised as beauty essentials. The sophistication emerges in the details. At the Temple of Hathor in Dendera, wall carvings depict what appear to be cosmetic laboratories, where priestesses ground minerals with moon-shaped mortars, a ritual tied to the lunar cycles they believed enhanced the mixture's potency. Recent excavations near Abydos uncovered a 3,600-year-old cosmetic manual on papyrus, listing ingredients like crushed lapis lazuli for its anti-inflammatory properties and honey as a natural preservative. Some eyeliner recipes even included allium garlic family extracts, now known to have antibiotic effects, suggesting an empirical understanding of germ theory millennia before its official discovery. What's truly revolutionary is how these formulations endured. Roman physicians like Galen later prescribed Egyptian kohl for eye diseases, while Coptic medical texts from the 6th century AD still referenced pharaonic recipes. Today, researchers at the Louvre and Cairo University are collaborating to decode these ancient patents, isolating compounds that could inspire new antibiotics as modern pathogens grow resistant to conventional drugs. The irony is profound. In our high-tech quest for medical breakthroughs, we're circling back to solutions that once lined the eyes of Tutankhamun. Beyond biology, these cosmetics wove science with symbolism. The almond-shaped eye motifs seen in hieroglyphs weren't just artistic flair. They mirrored the actual application techniques that maximized kohl's protective coverage. Sacred texts describe makeup application as a daily rebirth ritual, with each stroke invoking the eye of Horus to ward off evil. This wasn't superstition. It was a holistic approach where chemistry and spirituality merged seamlessly. When Cleopatra adorned herself with ground pearls and gold dust, she wasn't merely accessorizing, she was armoring herself against the world, one scientifically blessed pigment at a time. The legacy of Egyptian cosmetics challenges our modern divide between medicine and beauty. In a world where we compartmentalize makeup as aesthetic and drugs as functional, their approach seems startlingly advanced. Perhaps the true brilliance of these ancient chemists wasn't just in what they created, but in their recognition that wellness and artistry aren't opposing forces. They're two sides of the same mirror, each reflecting a different facet of human ingenuity. As we analyze their alchemy through 21st century lenses, we're left wondering how many other ancient beauty secrets were actually sophisticated health technologies in disguise. From forgotten computers to rust-proof metals, these 24 tools shatter the illusion that ancient civilizations were primitive. They weren't just ahead of their time, they were ahead of our time in ways we're still struggling to comprehend. The Antikythera Mechanism's celestial calculations, the self-healing properties of Roman concrete, the nanostructures hidden in Damascus steel, each one whispers a startling truth: human ingenuity isn't linear. Progress doesn't always march forward. Sometimes it loops back on itself, leaving behind fragments of brilliance we're only now piecing together. Think about what this means for history's so-called Dark Ages. Periods we've dismissed as backward might have been bursting with innovations lost to war, natural disasters, or simply the fragility of human memory. The Baghdad Battery hints at experiments with electricity that vanished for millennia. The precision of Inca stonework suggests engineering principles we can't replicate without modern tech. Even something as mundane as Mayan rubber reveals a mastery of chemistry that industrial societies would spend centuries reinventing. These aren't anomalies, they're evidence of entire threads of knowledge snipped from the tapestry of time. And here's the most thrilling part: we've barely scratched the surface. For every artifact displayed in museums, countless others lie buried or misinterpreted. New technologies like LiDAR are revealing lost cities under jungle canopies, while advanced imaging techniques are uncovering hidden texts beneath medieval manuscripts. Who knows what else awaits discovery? Perhaps another Antikythera-like device rests in an unopened tomb, or a scroll detailing forgotten medical breakthroughs moulders in some desert cave. The past isn't a static record, it's a living puzzle, and each piece we fit into place forces us to redraw the map of human achievement. This isn't just about rewriting history books. It's about humility. In an age of artificial intelligence and space exploration, we're reminded that our ancestors without satellites or silicon chips solved problems that still stump us today. They cured infections with makeup, predicted earthquakes with bronze dragons, and maybe even took to the skies with paper balloons. Their achievements demand we ask harder questions. What else did they know? And what could we learn if we stopped assuming their world was simpler than ours? So the next time you walk past an ancient artifact in a museum, look closer. That unassuming clay pot or weathered blade might hold secrets we've yet to decipher. The story of human innovation isn't a straight line, it's a spiral, winding back to truths we once knew and forgot. And if these 24 tools teach us anything, it's that the next great breakthrough might not come from a lab or a startup, but from the pages of a crumbling manuscript or the depths of a newly unearthed ruin. The past isn't finished speaking. Are we listening? Now it's your turn. Which of these ancient inventions shocked you the most? Do you think we'll ever recover lost technologies like Greek fire or the full potential of the Antikythera mechanism? Drop your thoughts in the comments, and if you're hungry for more mysteries, hit that subscribe button, because history isn't just about looking back. It's about discovering the future hidden in plain sight.